All right. So we're just gonna work through some problems today. Uh, work through a few problems. Let me see. All right. So let's start with problem. Oh, we already did one like that. Well, let's start with problem B right here. And then we're gonna do problem C over here. And then 742, 743, 741. Yeah, let's do that. So let's start with problem 861B. That's highlighted. And we'll do A over here too. So it says predict the major products of each of the following E2 reactions. So what do we know automatically without even thinking about it? What type of reaction are we looking at? Right, we're looking at an E2. So what do we know about the E2? Or let me say, what should we know? And how do you um, what's the strategy for predicting the products? It's not asking for the mechanism.
Not sure, Dr. Russell.
So the strategy is to find the leaving group and the alpha protons. The leaving group is here. The alpha carbons, the carbons next door to that leaving group are here and here. So we should get two. This is almost identical to the problem we worked on Wednesday. Was it Wednesday? May have been Monday. I think it was Wednesday. And every elimination is going to give you a pi bond. And the E2, you need a strong base, right? And it's giving you right here that sodium hydroxide is a strong base. So that's all of those are clues toward that, but the problem actually told you that it was an E2. So with the E2 elimination, we should get this product. That's one product that we should get. Start over. Right where the double bond is here. And the second product, the double bond should be on the other side. Right, if it's an E2, you're going to look for certain things. You're going to look for a strong base. Right, that's normally the giveaway, the base. If you see the base, you know it's an elimination. And then bromine, that's just a good leaving group. And which one of those two is the major product, according to Zayzev's rule?
The one
The most.
The one that's more substituted? Which one would that be? The one on the left that's
the
highlighted, or on the right?
the right.
So this is major, and then this is minor. All right. And this other base right here, sometimes you may see this base is potassium terpetoxide. It just looks like this. It's an oxygen with a terpetal group attached to it. Very strong base. I think it was actually in that elimination video that I sent. Right. So very, very strong base. So if you see that, NaOH, KOH, any type of base, any type of amine base like Na, NH2, all of those bases are going to be uh, used for E2 elimination. So I'll just write those common bases down here. So NaOH, KOH, potassium terpetoxide, NaNH2. All those bases are used to do E2 elimination. All right, let's go to 741. Let's do D, C, and A. We're gonna start with A. For each of the following pairs of compounds, identify which compound would react more rapidly in an SM1 reaction. That's the key to the problem right there. So you have to know what happens in an SM1 reaction, like what the mechanism is. What's the first step? The first step in an SM1?
The leaving group leaves.
Loss of leaving group. And then after that happens, you form a carbocation intermediate. So that the rate of that reaction is going to be based on how good your leaving group is or how stable your carbocation is. One of those two factors. So your rate is based on leaving group ability, which is based on the pKa of the conjugate acid. And I'm just going to abbreviate this, carbocation stability. Right. So with those two things in mind, if you look at A, which one of those do you think is going to be faster? And why?
A, because one is on a tertiary. It's a tertiary carbon.
So this one is going to be faster. Yes, it's a tertiary carbon. And that's what you're comparing, right? You're comparing the substrates because the leaving groups are the same in both cases. So you can't compare the leaving groups because they're the same atom, right? So in this case, it's a tertiary carbon versus a primary carbon where your leaving group is. All right. What about for, let's look at D, right? What are we comparing in that case? Because both of those substrates are tertiary.
The leaving groups.
Leaving groups, right? You got a chlorine on one, you got a tosylate on one. If you compare them, if we go up to our chart, I hate to back up all the way up to here, but we can do it. If you go up to our chart right here, all our leaving groups are right there. right? And this leaving group right here is the tosylate. Right, that's what you see abbreviated as TOS or TS. Right, it's toluene sulfonate. The toluene part is this the ring back here, and then the sulfonate part is obviously the sulfur part. So that's why we call it a tosylate. Right, and you can see the pKa of the conjugate acid is negative 0.6, and then for chlorine, it's negative 7. So which one do you think is going to be faster? One with the tosylate leaving group or the chlorine leaving group? Which one of those conjugate acids has a lower pKa? Which one is further away from 0?
Yeah.
Negative 7 or negative 0.6?
-7.
Yeah. So the chlorine substrate is going to be faster. Right. So the pKa of that conjugate acid is negative 7, and then the pK. That's how you compare leaving groups. You just look at the pKa of the conjugate acid. So it's negative 0.6 for that. All right, what about C? What are we looking at for C? Same leaving group, different type of substrate. So what are we looking at for C?
Would it be something to do with hires?
Yes. So let's look at the two carbocation intermediates for C. All right, so this one will look like this with a plus charge right there, and this one would look like, sorry about that. Like that. So the question is, what can you do with that carbocation on the right that you can't do to the one on the left?
Resonance.
You do resonance because it's a allylic carbocation, right? So this will be resonance stabilized. Come on, pen. Right, that's a resonance stabilized carbocation. Again, your rate for SN1 is going to be based on the leaving group ability as well as the carbocation stability. So that resonance stabilized carbocation is more stable. It means it's going to form faster than the carbocation on the right, which is just a secondary carbon. All right. Let's look at any questions about that before we go to another problem. All right. So part A, 876A says propose a mechanism. So what do you think? What kind of reaction happened in A? Looking at the product.
Elimination.
Elimination. The question is now what type, right? Is it E1 or E2? And based on what we know about the elimination mechanisms, which one do you think it is? Based on the conditions.
E1.
It's E1. That's right. You can't do you need a base to do E2, and you're doing this in the presence of an acid. So this is an E1 elimination. All right, what about C? Look at the product, look at the conditions. Do you think it's E1 or E2?
Is it also E1?
It's also E1. Yeah, don't be scared. You, you're right. It's an E1 elimination. It's done in the presence of, it's an elimination, but it happened in the presence of a strong acid rather than a strong base. So it's E1. Uh, but the outcome is not the expected outcome. And that's one of the, uh, I don't want to call it a drawback, but that's something that can happen when when you're forming these carbocation intermediates. Is sometimes you can get some rearrangement that happens because you can see based on the starting material, the expected product should be this. Right, you would expect to get this. Well, this is here. There's no proton there, so you expect that. Right? Do you see it? And why am I eliminating there? Right? If you look at where your leaving group is, your OH, even though it's has to be converted first into a better leaving group, it's still a leaving group. Right? Where are your alpha positions to that O? Because that's where elimination happens. It's always at the alpha position to that leaving group. So where is the alpha position based on where that OH group is?
On both sides of
On
the
both sides.
OH.
Yeah, it's at this carbon and that carbon, right? Now the carbon up top, are there any hydrogens on that carbon that can be removed? Or does it already have a full octet?
Full.
It's full. No hydrogen. So that's why your alpha proton has to come from here. Right? Because there's no alpha protons up top. So then we see now, right, that the expected product should be this alkene that I have drawn down here, but that's not what you get. So if we look at how this happens, then we can figure this out. So that's that. You got OH here. And then we're gonna react that with sulfuric acid. Right? We already agreed that it's an E1 because it's done in the presence of acid. So this is coming here and here, right? So we're going to protonate oxygen. So now this is water. And it's positive. Right? And then that's going to leave, because that is my leaving group. That's going to leave and leave me a carbocation intermediate. Right there. Sorry about that. And that's not a radical. Close this up. Sorry. This glove, and between this glove and this stylus, and I promise you, whoever made this glove, I could slap him twice. All right. So now when we look at the that intermediate, what type of carbocation is that? How would you classify it as far as the substitution pattern is concerned? Is it primary? Is it secondary? Is it tertiary? And don't forget, there is a, let me put this in too, because that's going to help us solve this problem. There is one hydrogen here, right? So what is primary, secondary? What do you think? You should know this. It's definitely not primary. And it's definitely not tertiary. So it's a secondary carbocation. Right? So sometimes when you have a secondary carbocation like that, whether you're doing SM1 or E1, if you got this carbocation intermediate, and you can make that carbocation more stable through a rearrangement or some other process, then that's what's going to happen. And so what happens in this case is you do a what's called a methyl shift. Right. So one of these methyl groups up here, and I'm just going to write it over here. Right? You're going to shift the carbon and its electrons. So the whole group shifts over, and that's going to give you a more stable carbocation on the carbon that's shown up top. Right. So this whole CH3 group is going to move here. And I think we talked about this in right. So that whole methyl group is going to move. And the reason behind that is to give you a more stable carbocation, right? You go from a secondary to a tertiary. So now that's still there. Now that carbon is positive. Then you have the other methyl group that moved here. And the hydrogen is still here. Right? And then it's this carbocation that is going to undergo rearrangement. Not rearrangement, elimination. Right. So how do we do elimination? When we talked about the E1 the other day, what facilitated the elimination part? Like how do we remove that proton? Anybody remember that? This was Wednesday when we talked about this. Was it the conjugate base from the initial proton transfer? So the conjugate base from sulfuric acid, what you'll get after that first step. Right, so it's that conjugate base that's going to come in and remove that proton. So I'm just going to abbreviate it here. Right, so that's where the elimination is going to take place. And then you end up with this product and not the expected product, all because of that rearrangement of that secondary proton, right? So a methyl shift is a type of rearrangement. I don't know what's going on with this freaking screen, man. Come on, bro. Killing me. All right. I would ask if there are any questions, but I don't think I don't think there are any. Let's just move on to 742. I'm gonna let y'all deal with this one. I'm gonna stop recording just in case it's too quiet. But this is something that
And then B, how would the rate be affected if the concentration of the sodium cyanide is doubled?
all right. What do you need to know in order to answer those questions?
The rate constant and which mechanism?
You need to know the mechanism. If you know the mechanism, then you'll know the rate law. Is that right? So
Yes.
which mechanism is this reaction going to proceed through? And how do you know? Right? You have some things you look for. You look for what type of substrate you have. Is it primary or secondary or tertiary? Then you can look at your solvent. Is it protic or aprotic? Then you can look at the stereochemistry in the product. Is it inverted or is it racemized? Like all of those clues point to tell you which mechanism is plausible. So what do you think? If you look at the all the conditions we just talked about, the substrate, which is secondary, the solvent DMSO is polar aprotic, and then look at the product. It's the stereochemistry is inverted. What do you think? Is it it's not an elimination because there's no alkene in the product. So it's got to be one of the two substitution mechanisms.
I think it's SN2.
SN2. Right? All the conditions point to SN2. The fact that you have reverse stereochemistry, that's the biggest giveaway. The inversion of stereochemistry. But then you're doing this in a aprotic solvent and you're doing it on a secondary substrate. Remember, secondary substrates can do either or. So you have to look at other conditions to tell whether or not it's SN1 or SN2. So what would the rate law be?
K equals substrate.
Okay. What does the 2 stand for in SN2? But you're right, the substrate is definitely involved. The 2 means it's bimolecular, remember? It's the substrate and the nucleophile that control the rate.
Okay, got it. Thank you.
Mhm. But thank you for contributing. Thank you for because then that allowed another point to be made. So the 2 and SN2 and E2 means that the reaction is bimolecular. So there's going to be a 2-term rate law, right? Not and then SN1 and E1 are unimolecular. So it's a 1-term rate law. So how would the rate be affected if you double the concentration of the substrate? That's the alkyl halide is the substrate. So if you double the concentration of the substrate, what's going to happen to the rate? Go ahead. Don't just say it. It's fine. It's okay if you get it. If it's wrong, we get it corrected. If it's right, then more power to you. I heard it, but can you say it again?
It would increase.
It would increase. It would increase by how much? Think about this, right? So the rate is the concentration is understood, unless it's given, it's understood to be 1. But in this case, it's saying, let's slap this thing. In this case, it's saying that you are doubling one of them. Right? And you keeping 1 constant. What is 2 times 1?
2.
2. So what should happen to the rate? It's going to increase for sure, but by how much?
2.
Yeah, it's going to double. If you double the concentration of any one of your, or not anyone, either one, if you double the substrate or the nucleophile, right, the rate is also going to double. What about the second question? How will the rate be affected if the concentration of the nucleophile, sodium cyanide, is double?
For some reason, if I'm remembering correctly, it would be the opposite. It would like decrease.
Why would it decrease? Did it decrease up top?
Maybe I'm not remembering correctly. Maybe it would increase.
It should increase. It's the same rate equation. It's just a different one of your the other term is now double. You know what? I going to go back to my old method of just using my finger. That'll solve everything, right? So it's the same. It's going to double because it's the same rate law, right? If you double one or the other, the rate is going to double. If you triple one or the other, the rate is going to triple. What happens if I double both of them? I think we talked about this. I can't remember which day it was. Maybe when we did E2. That might have been Wednesday. What about double them both? What should happen to the rate?
Would it increase by 4?
It will quadruple.
Oh.
What if I triple them both?
Then by 6?
No, it's a product.
So 9.
Yeah, so about 9 times. What if I quadruple them both?
16.
These 16 times rate increase. So that's how that works. If it's a bimolecular rate law, whatever I do to one term or the other is going to affect the rate. Whether I double it, half it, cut it by a third, whatever, it's going to affect the rate in that way. Right? Let's look at the next one. Same type of question. What mechanism do you think is operating here? Like, how am I getting from that alcohol to that alkyl halide using HBr? It's a substitution for sure, right? Because I swapped out the OH with the Br. But how did I get there? We only know right now 2 substitution methods. So it's got to be one or the other. It's either SN1 or SN2. And why wouldn't it be SN2?
It wouldn't be SN2 because it's too bulky?
Well, yeah, that too. It's tertiary. That too. So that's one of the reasons why it couldn't be SN2. So you're right. What else? There's another reason. What am I doing?
Oh, it's in a protic solvent.
It's protic. HBr is protic. It's an acid. So if I added a nucleophile to this, that the acid is just gonna solvate the nucleophile and nothing's gonna happen. But the fact that it's tertiary matters too, right? It's too bulky to do SN2, but then at the same time, it's a great substrate to form a carbocation intermediate, which is exactly how this reaction works. This is something that we did already when we talked about conversion of alcohols to alkyl halides, right? If you protonate oxygen, you lose it as water, you have a carbocation, and then bromine comes in and replaces it. So we know it's SN1, right? So now that we know it's SN1, how do we answer those 2 questions? What's the rate law?
Now this one is K equals substrate.
K, yeah, the rate is K times the substrate. That's exactly right. That's exactly right. So it has nothing to do with the HBr. It has nothing to do with anything else. It's just the substrate. So what happens if you double the concentration of the substrate, which is the alcohol? That's the substrate is just another term for your start material, right? Which is the alcohol. What happens if you double it? What happens if you put a 2 in there in that bracket? What's going to happen to the rate?
It'll be 4.
Well, it can't be 4 because I'm not multiplying this by anything, right?
I'm not.
So if I double this concentration, then the rate should also double. Whatever I do to the concentration of that substrate, that's what's going to happen to the rate. If I double it, triple it, cut it in half, increase it by 10, whatever I do, that's the effect that you're going to see on the rate. So
Okay.
if I double the concentration, then the rate is going to double. If I triple it, then the rate is going to triple. If I quadruple it, then the rate will quadruple. You following?
Yeah.
Yeah. So it would double. What about B? What if I double the concentration of HBr? Look at the rate law before you answer though. Is HBr included in that rate law? Is the nucleophile included in the rate law? Even though that's not a nucleophile, it's a latent nucleophile.
No.
No. So I could increase the concentration of HBr by 1,000 and the rate won't change because the rate is based on the loss of leaving group from the substrate for SN1 substitution. It's not based on anything else. So I can increase that by 1,000,000 and it's not going to change, right? So the answer here is nothing, right? Nothing is going to happen. All right. Any questions about that? All right. I got one more question that I wanted to talk about. I don't know if I'm going to have time. So what I'm going to do, I want you to do these on your own 750. All right. And these are all substitutions. So all you're doing is swapping out the nucleophile with the leaving group. So in each one of these cases, leaving group, leaving group, leaving group, leaving group, leaving group, leaving group. And then your nucleophile is given. For this one, it's not the sodium now, it's the cyanide. That carbon has a pair of electrons and a negative charge. Right, for this one, if you put some electrons on sulfur, sulfur is the nucleophile. And if the product is charged at the end or whatever, it's okay. Right, just like here, so anytime you see a sodium or some metal, that's just a counter ion. Right, it's the oxygen that's the nucleophile. And that's negative. All right, so I want you to work on those on your own 750. And then 755 is what I wanted to talk about. But I'm going to send you, this will be the last set of videos you get. And we'll just, I want you to look at this over the weekend. And we'll talk about it on Monday. It's going to be very short. But I'm going to send you the ranking nucleophiles video so you can take that quiz too. And then this is the last question that we'll do on, this and maybe 834. Maybe we'll do one question off of that. And then we'll be done with this section and we'll be ready to start another section on Monday and then test on Friday. So, yeah, so let me stop recording and then